Let's start illustration number 5. As shown in this figure, a block of mass m moves with the constant velocity under the influence of force F, which is acting in the direction making angle horizontally. If the frictional force between the surface of the block and the horizontal surface is Fk, then we have to find out the distance of action of normal reaction, that is capital N, from the origin O. So we have to actually find out this distance. And here the block does not perform rotational motion. So what is the main disadvantage of it is not rotating or it is not in rotational motion? So there is one advantage also and one disadvantage. So the disadvantage is we have to find out the value of force for each and every particle of this box, and the another advantage is that this box is said to be in rotational equilibrium. The box or the block is in the rotational equilibrium. And in this condition, we know the resultant force and the resultant torque will be 0, and so I am consider over here first of all the resultant torque. So the first torque which will act on this is Fk at 0, means R cross F. So first of all the frictional force at origin. At the length L by 2, the force is acting in the negative direction, and that is minus mg. At the half of the length, that means L by 2. Plus, if you see over here at the same length of L by 2, there is a normal reaction is also acting. So plus n of x, and the next one is the force F in the horizontal direction. So the angle is theta, the parallel component will be minus F cos theta, which will be multiplied with height h. Similarly, in the downward direction, or we can say at the vertical direction, the force which is acting is F sin theta into L, that is equals to 0, because the resultant torque of the system we have to consider as 0. And now let's simplify this equation, and after simplifying we will get the value of nx. So all other values are on right hand side. I am putting n of x, that is equals to mg into L by 2 plus h into f cos theta, and here the positive sign will go on the left hand side, and so there is a change of sign, and hence the right hand side will be minus L into f sin theta, and this equation I am denoting as number 1. And now for translation equilibrium stage, we have one relation that mg is equals to n plus f sine theta. If you remember, then this relation we have obtained in the semester 1, and the f cos theta, that means the parallel component, will be related to the frictional force of the surface, that means Fk, and therefore the value of n will be from this equation mg minus f sine theta. So this is the equation number 2. Now let's substitute the value of this equation number 2 into the equation number 1. So therefore I have now only the value of n. So I am putting mg minus f sine theta into x is as it is, and the right hand side is also as it is. So mg into L by 2 plus h into f cos theta minus L into f sine theta. So now I have to find out the displacement. So let me make this x as an object, and so the value of x is equals to mg into L by 2 plus h into f cos theta minus L into f sin theta, and this term is divided by the co-multiplier of x, that means mg minus f sin theta. So this is the actual value of displacement of the block under the influence of given forces. And remember, this is not the case of rotational motion, and you may have noticed we have not used any kind of equilibrium equation over here, just the condition has been used, not other equation. Otherwise this is the problem of classical mechanics, and in that particularly this is the problem of such kind of linear motion. Illustration number 6. If we accept the earth has a solid sphere of uniform density and imagine that it contracts so that the radius becomes half without change in mass. So first of all, I am consider my analysis with the assumption that if the resultant external torque on the earth is 0, then one quantity is constant. Whenever the tau is 0, we know that according to the law of conservation of angular momentum, the value of capital L is constant. And so, if you use the equation which is given in this way, L is equals to I omega for two different cases, then its right hand side can be determined as I1 omega 1 is equals to I2 omega 2. Now, for the solid sphere, if you want to find out the value of moment of inertia, I is equals to 2 by 5 m r square, and this is about its diameter, where here m is equals to the mass of the sphere, and this r refers for the radius of the sphere. And now I am substituting this value of I in equation 1 by providing the subscripts. Therefore, 2 by 5, the mass will remain constant, only the radius will be changed. So 2 by 5 m1 r1 square omega, and the value of I2 is 2 by 5 mr2 square omega. And now we know that the value of radius is being half without change in its mass. So I am supposing that the value of in first case radius is getting half. Therefore 1 by 2 r1 is equals to r2. That implies r1 is equals to 2r2, and I am substituting this value in this equation. So what I will get? First of all, this 2 by 5 will cancel out. Here omega 1 and omega 2 are as it is. These m values are cancelled, and instead of r1 now I am substituting 2r2. Therefore here the square will be 4r2 square omega 1 is equals to r2 square omega 2, and therefore the value of omega 2 is 4 omega 1 because these r2 square are cancelled from both the sides. Thus, the new rate of rotation, that means omega 2, becomes 4 times the present rate of omega 1, and hence the day of 24 hours will become its 1/4, so the day will be of 6 hours. And with this, illustration number 6 is over. Now, let's start the new topic, radius of gyration. Let's start the illustration number 7, in which we have to find the moment of inertia about an axis passing to the end and perpendicular to the length of a rod. So this is the simple example what we have considered in the above theory. Here I am assuming that the mass of the rod is capital M, and also the distance of the end from the rod and from the origin is d is equals to L by 2. And we know, according to the equation of moment of inertia of such kind of rod is given by the moment of inertia of its parallel axis, and the value is ml square by 12. So this is 1. But here the value of d is provided to us, and the total moment of inertia I is equals to IC plus MD square, and here the value of IC is ML square by 12 plus M is as it is the value of D is L by 2. So L by 2 whole square, that is equals to ML square by 12 plus ML square by 4. And so if we take the LCM, then here ML square is as it is, here 3ML square divided by 12, that is equals to 4ml square by 12. So the final answer will be ml square by 3. So this is our moment of inertia. Now comparing this equation, that means I is equals to ml square by 3 with the equation I is equals to mk square, what we have obtained in the theory of relation between gyration and moment of inertia. So with the help of this equation, now I have the value of k square is equals to L square by 3, and therefore the value of k is L upon under root 3, and that is the radius of gyration. Now let's move on to the next example, illustration number 8.